So you both have done so much research on climate change to better help us understand it. Tell us about your research and tell us about your trips.
We're ice core paleoclimatologists, which means that we use the ice cores that we've collected around the world to tell us about what Earth's past climate has been. And we do this by measuring the various chemical species and the dust and the pollen and everything that falls out on a glacier eventually becomes buried, just like a multi-layer cake, and the oldest layer is at the bottom and the youngest layer is at the top, and we come along with our drills and we drill through that and we get a history or a record. Most of my work is in the polar regions, Antarctica and Greenland, and Lonnie has been working for the last, as I have, for the last 40 years, but he works in the low latitudes on the glaciers that are on top of some of the world's highest mountains.
Yeah, I think I've had the pleasure of working in 16 different countries, drilling ice cores, getting to know the people, setting up the logistics. And by doing this around the world and having these records also from Greenland and Antarctica, we can start to put together a global picture of how climate has changed. And we're particularly interested in things like how's the temperature change? I mean, our instrumental records only go back 150 years. We know climate varies on much longer time scales, and what the ice does is provide us a perspective of those changes. And there are very few archives that actually allow you to determine how much precipitation fell in the past. But by measuring the thickness of these layers, we can determine the year-to-year variability in precipitation in these diverse parts of the world. So they're fantastic records.
Let's drill down a little bit, no pun intended. Explain what actually is an ice core, how do you drill them, and what exactly are you looking for in the ice cores?
Well, the ice core is a cylinder of ice. The size of the cylinder depends on the drill, and we design our drills here. They have to be lightweight portable systems to take them up to 20,000 feet on a mountain range. So every piece has to be portable. And in the ice cores, we cut them about 3 feet in length. They go into a special bag, and they're labeled so we know where they fit in the sequence. They go into a special tube, and then they go into insulated boxes, and they have to be kept below freezing for the whole transit out of these remote parts of the world. Okay. And we now have over 4.5 miles of ice in our freezers downstairs, and they come from parts of the world where the glaciers that I drilled earlier in my career are now gone. So they're one in only ice cores.
All right, so you have miles and miles of these ice cores. They're each roughly 3 feet long. What are you actually looking for in these ice cores?
In the Greenland ice cores, because Greenland is downwind of North America, we can actually look at the Greenland ice cores and tell, for example, when the United States implemented the Clean Air Act in 1970. We can monitor all those pollutants from the Industrial Revolution. Up, Clean Air Act 1970, sulfate starts coming down.
Really?
We can look at nitrate and see nitrate is flat until about 1950. What was that? That was the Green Revolution, when post-World War II, think of the baby boomers, and population on the planet was just shooting up. And the fear was, how will we feed all these people? Oh, well, we're going to grow more food. Well, how do you do that? You have to use more fertilizer, nitrogen and phosphorus. That's what you use. We measure that on the Greenland ice sheet. But you can go back and actually look at like smelting different metals. And in Peru, that's particularly been interesting.
Tracing back to the Incas and when they were smelting,
Exactly.
You can actually correlate that history
Yes.
through an ice core and talk about what happened.
Well, and these are interesting questions because we know when metallurgy started in Europe and those parts of the world, but we don't in South America. And yet in the ice, there's a history of the heavy metals that come from smelting.
Sure.
And so you can document that.
So talk to us about that, because you made the nice correlation between measuring these different ions and these particles and these molecules to give you kind of a historical representation of what happened in people. Make the link to climate change. What are you looking at in there that's telling you, wait a minute, our climate is actually changing?
We measure the oxygen and hydrogen isotopes. That's one of the key measurements that we make. The temperature in the atmosphere when the water vapor condenses and the snowflake forms, and then the snowflake falls out on the glacier and it's buried. That carries with it the temperature record. The other thing that the ice cores provide is the history of the composition of our atmosphere. That's the beauty of the ice cores, is that these bubbles get trapped in the ice and they contain ancient atmosphere. Carbon dioxide is one of the major greenhouse gases that we're concerned about. If you keep increasing the concentration of that in the Earth's atmosphere, the Earth loses its capacity to cool itself. So we know what the important greenhouse gases are, but if you look at the history of those greenhouse gases as provided from the ice cores, you'll see these glacial interglacial cycles of about 100,000 years, and then you come up to the last 150 years, and then you look at those gases go up, and where we are now, you can project that back 800,000 years, almost 1 million years, and never has the CO2 risen above around 300 parts per million, and we're at 415 now. And we know what these gases do to the climate. So that's proof positive that it's human activity that's driving much, not all, but much of the changes that we're seeing with the warming of our planet.
With that, is it reversible? What can we do in terms of our daily behavior, monthly behavior, yearly behavior as individuals and as countries to help reverse that, if it is reversible?
It's a multifaceted solution. We have to slow our emissions. We have to come up with technologies that help us take those gases out of the atmosphere. We can't wait for the biosphere and for nature, essentially, to absorb all those and utilize those. We need so many people working on this problem from so many different disciplines and perspectives. We need our engineers. We need all those young people out there to help us. And I say us, I mean the scientific and engineering communities, to solve this problem.
Humans have had impacts on our environment as long as we've been here. It's just that today we have 7.8 billion of us, and we're having a huge impact. So the human activity on the planet is recorded in these annual archives that are on these mountaintops and in these polar ice fields. The problems that we face are international problems. They can only be solved by working together. How do we learn to adapt to the change that is coming? And we can only do that by communicating and working together.
Well, I have to say, you guys may specialize in ice cores, but you have a warm heart, and I guarantee you are an inspiration for the next set of scientists that you said
Well, we're going to need them.